Hello and welcome to my presentation on development of a ductile damage model implemented within creep crack growth simulations of 316H stainless steel. So to give a quick overview of the presentation, I will start by outlining the background to the problem and the motivation for carrying out the work that we've done. I will then go through the notch bar testing process and its results, which were used to develop a ductile damage failure locus. Following on from that, I will talk about how this ductile damage model was implemented within a creep crack growth simulation. Then I will discuss the results, highlighting further improvements that need to be made, before finally concluding. So first I'm going to give some motivation and background for why we're doing this research. Creep deformation occurs in high temperature applications such as boilers in nuclear advanced gas-cooled reactors. Once an appreciable amount of creep deformation has accumulated, cracks can initiate at floors. The growth rate of these creep cracks is often characterized by the fracture mechanics parameter C star. This cannot be determined directly from its line integral definition in an experimental test, apart from on the surface of a sample, which is not representative of the full thickness of a high constraint geometry, such as a compact tension specimen. It therefore must be calculated using the expression shown, which relies on determining delta.c, the creep contribution to the load line displacement rate. The load line displacement must be partitioned in order to determine delta.c, as shown here. The total load line displacement rate is measured in a test, and the elastic and plastic contributions can then be subtracted from this to determine the creep contribution. A novel method for displacement rate partitioning has recently been developed which calculates the elastic and plastic contributions through FEA simulations. This method modelled creep cracks as being continuous, but they are in fact discontinuous, as shown by this X-ray CT analysis of a creep crack. This shows how the crack morphology varies considerably across the crack front. And this shows in red the voids that make up a creep crack. We postulated that because creep cracks are so discontinuous, there would be intact ligaments of material behind the crack front which would likely experience very high stresses. This could lead to failure of the ligaments due to ductile rupture. It is desirable to be able to capture this within the FEA simulations so that the contributions to the load line displacement can be accurately determined. The ductile failure of the material is dictated by a locus of multi-axial failure strain as a function of triaxiality. It was necessary to formulate this locus through multi-axial tensile testing of notch bar specimens of the material, which in this case was 316H stainless steel. Three different notch geometries were used in the testing: a sharp notch, a medium notch, and a wide notch, the dimensions of which are shown here in millimeters. The required outputs from the testing were the strain at failure and the triaxiality exhibited in the notch. These values would be determined using expressions derived from the work of Bridgman. In order to determine the strain and triaxiality, it was necessary to take measurements of the specimen cross-sectional radius and notch radius of curvature throughout the test. These measurements were taken through image capture of the specimen. A furnace with a window was used so that the specimen could be maintained at a temperature of 550 degrees C. The images were taken every 2 seconds using a Nikon D7200 with a 200mm lens that was capable of a maximum aperture of f4. The images taken in the tests were first post-processed using Ductile to enhance the contrast between the specimen and the background. The images were then thresholded to give binary black and white images. This allowed for clear determination of the specimen edges and subsequently the specimen width. The images were analysed using a MATLAB script to give values for the strain and triaxiality throughout the test. An example of the distribution of strain against triaxiality is shown here for each of the three notch geometries. In all cases, the triaxiality decreases with increasing strain for most or all of the test, as the notch radius increases under tension. In the wide notch, the triaxiality increases towards the end of the test. This is because localized necking occurs in the center of the notch, so the minimum notch radius begins to decrease. The triaxiality values were averaged with respect to the strain throughout the test to give a single mean triaxiality value. These were plotted against the corresponding failure strains normalized by the uniaxial failure strain to give the failure locus shown here. The value at the top left is from a uniaxial tensile test. A power law expression was fitted to the experimental data to predict the multiaxial failure strain as a function of triaxiality. The Rice and Tracy model is also shown here, as it is commonly used to model ductile damage in metals. It can be clearly seen that this would not accurately predict ductile failure for 316H under these conditions. This empirical power law expression was implemented in an Abacus FEA simulation by means of a Fortran user-defined field subroutine. The damage was modelled according to the commonly used ductility exhaustion formulation shown here. Under this formulation, the damage accumulates until the parameter is equal to unity, at which point the material is considered to have failed. This failure is represented in the simulation by reduction of stiffness in the affected element. Creep crack growth was simulated in a compact tension specimen. A 2D plane strain model was used, as it has been previously shown that 2D plane strain closely represents the stress state of a 3D specimen, as shown in this graph. A half model of the CT specimen was simulated, making use of its symmetry in the y direction. The crack growth mesh is shown here with a fine mesh in the crack growth region and a much coarser mesh over the majority of the specimen to reduce computational load. The dimensions of the specimen are shown here. The applied load was 90% of that of the limit load for this geometry in plane strain, and the test duration was 1000 hours, which is relatively short term. Currently, it is not possible to capture the exact path of a discontinuous crack as it grows throughout time. As such, it was necessary to fabricate the growth profile and its route to approximately represent how it would be likely to grow under the given loading conditions. The crack length as a function of time is shown here. The crack growth was implemented by progressive removal of individual elements from the model until it reached the full length of 2 mm, as shown here. The elastic behavior of the material was modelled by using a value of 140 gigapascals for the Young's modulus, and the plastic behavior was modelled using experimental uniaxial tensile data as shown here. The optical profile analysis technique was used for the uniaxial tensile test, which meant that it was possible to characterise the high stresses and strains that are exhibited in the neck right up until failure. This technique shows a marked improvement over standard extensometry, which can only capture strains up to the point of necking, which for this material would occur at around 40% strain. Both the primary and secondary creep behavior of the material were modelled through a user-defined creep subroutine. This made use of discretized forms of the commonly used primary and secondary creep expressions, shown here. The procedure for the simulation followed a scheme of alternating static and visco steps. The specimen would be initially loaded up in a static step, which would only exhibit elastic plastic behavior. A visco step would follow, which would allow the specimen to deform by creep. The duration of this step would be until the crack initiated. At this point, the visco step would end, and another static step would take place, in which an element would be removed from the model to simulate crack growth. A visco step would then follow, allowing for further creep deformation until the crack had grown by the length of an element, in this case 0.02 mm, and then another static step would occur in which another element would be removed. This alternating process repeated itself until the full crack length of 2 mm had been attained. The benefit of this method is that in the static steps the specimen will only deform in an elastic plastic manner, and in the visco steps it will only deform by creep. The separate contributions to the load line displacement can therefore be easily extracted from each of the two different types of step. Ultimately, no elements were fully damaged by the end of the simulation, the reasons for which will be discussed shortly. Here are the contributions to the load line displacement, both elastic plastic and creep. It can be seen that the elastic plastic contribution is larger than the creep contribution, but most of the elastic plastic deformation occurred on load up. This graph shows the contributions post load up, and from this it can be seen that once the load had been applied, the majority of the deformation was due to creep. The reason for such a high creep contribution, roughly 37% of the total, is shown here. Because none of the ligaments broke, they were able to continuously deform by creep, and because the stresses in the ligaments were still high, the creep rate was also high. However, as can be seen, the creep strains are very localized and have led to considerable warping of the affected elements. The highest strains exhibited are over 220%, which is non-physical. Given that this investigation follows on from analysis which modelled the crack as being continuous, it is pertinent to compare the behaviour of a discontinuous crack with that of a continuous crack. It can be seen that the elastic plastic contribution for a continuous crack is much higher, and that the creep contribution is much lower. The reason for this is that if the crack grows continuously, the stress intensity is much greater, leading to higher stresses and more plastic deformation. Creep deformation also does not have the opportunity to occur as much if intact ligaments of material behind the crack tip are not present. So why did no elements fail by ductile rupture? Fundamentally, it is because neither the triaxiality nor the stresses reached high enough levels. The triaxiality rarely exceeded a value of 2, and with the failure locus used, this would only reduce the failure strain to 60% of the uniaxial value. Given the stress-strain behaviour of the material, a stress of roughly 750 megapascals would be required to attain this level of strain. The equivalent stresses were suppressed both due to the constraint caused by plane strain conditions and also by considerable stress relaxation due to creep, which meant that the plastic strain required for failure was not reached. However, as mentioned previously, the level of creep strain exhibited is not physically possible, and the ligaments that experienced these high strains would have ruptured, but creep damage was not implemented in this simulation. Therefore, various improvements to this model are necessary. It would be ideal to model the specimen in 3D, as this would likely mean that plane strain conditions are not imposed in the ligaments, given that they do not extend fully across the crack front, and therefore ductile rupture would be more likely to occur. It is also important to note that work by Bai shows that plane strain conditions lead to lower multi-axial failure strains than axisymmetric tension. So if the ligaments do in fact experience plane strain conditions, then the locus developed is not necessarily appropriate for this 2D simulation. In addition, the assumption that material only loses load-bearing capacity once it reaches its failure strain is possibly also flawed. As such, the damage formulation could implement some gradual decrease of the stiffness, as opposed to just losing all of the stiffness when it reaches a damage value of 1. To conclude, a novel optical profile analysis technique has been used to determine a ductile failure locus for 316H stainless steel at 550 degrees C. This locus was implemented by means of a Fortran user subroutine as part of a ductile damage model within a discontinuous FEA creep crack growth model. None of the material failed in a ductile manner, and this was likely due to suppression of the equivalent stress due to constraint and creep stress relaxation. It is therefore desirable to simulate discontinuous crack growth in 3D so that the appropriate level of constraint is applied to the material, and a more in-depth damage model should be used. Thank you for listening.